Hello, everyone. Welcome to our Deep Dive podcast, where we review the latest and most impactful research papers in AI. Today, we're exploring the paper titled Mini-o3, Scaling Up Reasoning Patterns and Interaction Turns for Visual Search. Are you ready to get started?
Absolutely. This paper is quite fascinating, especially because it addresses a major limitation in current vision language models, or VLMs. The authors point out that most open-source VLMs struggle with complex visual search tasks that require multiple reasoning steps and trial-and-error exploration. Isn't that a big deal?
It really is. Most existing models, like DeepEye's, perform well on simple benchmarks but fall short on harder tasks. For example, DeepEye's achieves only 35.1% accuracy on the Visual Probe hard dataset. The main issue is that these models tend to use monotonous reasoning patterns and only a few interaction turns per example. That's a significant bottleneck.
Exactly. The authors of Mini-o3 wanted to overcome this by scaling up both the depth and diversity of reasoning patterns. Their system, Mini-o3, is designed to execute deep, multi-turn reasoning, sometimes spanning tens of steps. That's a huge leap from the typical one or two turns we see in other models.
Right, and to achieve this, the authors introduce a three-part recipe. First, they construct the Visual Probe Dataset, which is a collection of thousands of challenging visual search problems. These are specifically designed to require exploratory reasoning, not just simple object localization.
The second part of their approach is an iterative data collection pipeline. They use this to obtain what they call cold start trajectories. These are multi-turn reasoning examples that include diverse strategies like depth-first search, trial and error, and goal maintenance. This diversity is crucial for training the model to handle complex tasks.
The third component is particularly interesting. They propose an overturn masking strategy during reinforcement learning. This prevents the model from being penalized when it hits the maximum number of allowed turns during training. That way, the model doesn't learn to answer prematurely just to avoid penalties.
That's a clever solution. It means that even though the model is trained with a cap of only 6 interaction turns, it can naturally scale to tens of turns during inference. And the results show that accuracy actually improves as the number of allowed turns increases at test time.
Let's talk a bit more about the Visual Probe dataset. Unlike previous benchmarks, this dataset features high-resolution images, small targets, and lots of distractor objects. That makes the tasks much more challenging and forces the model to use iterative exploration and trial and error.
Yes, and the dataset is split into 3 difficulty levels: easy, medium, and hard. The hard instances are especially important for encouraging the model to develop reflective and exploratory reasoning patterns during reinforcement learning.
Now about the cold start data collection. The authors found that training with reinforcement learning alone led to concise responses and very few interaction turns. So they used supervised fine-tuning with cold start data to activate the model's multi-turn tool use capabilities.
They generated about 6,000 cold start trajectories using a small set of manually crafted exemplars. These exemplars demonstrated various reasoning strategies, and the model was prompted to imitate them in a few-shot manner. Only trajectories that ended with the correct answer were kept.
That's a smart way to ensure high-quality training data. Now, let's discuss the reinforcement learning setup. The base model's context length is limited to 32K tokens, and with the default image budget, the number of interaction turns is severely limited. To address this, they reduced the maximum pixels per image, allowing more turns to fit within the context budget.
And then comes the overturn masking technique. In standard reinforcement learning, responses that exceed the turn or context limit are assigned 0 reward, which can penalize the model unfairly. The overturn masking strategy masks out these responses, so they don't contribute negative learning signals.
This is crucial because it prevents the model from collapsing into an answer earlier strategy. Instead, the model is encouraged to explore deeper reasoning paths, which is exactly what's needed for challenging visual search tasks.
During inference, they also found that greedy decoding led to repeated words or sentences, likely due to the growing context with more turns. Setting the temperature to 1.0 during generation helped reduce this repetition without sacrificing coherence.
Let's move on to the experimental results. The authors compared mini-o3 to several existing models on multiple visual search benchmarks, including Visual Probe, VBench, HRBench, and MME Real-World. Across all datasets, mini-o3 achieved state-of-the-art performance.
For example, on the Visual Probe hard dataset, mini-o3 achieved 48.0% accuracy, compared to 35.1% for Deep Eyes and 28.8% for Pixel Reasoner. That's a significant improvement.
The ablation studies are also quite revealing. They show that each component of the mini-o3 recipe, hard RL data, cold start supervised fine-tuning, and overturn masking, contributes to the overall performance. Removing any one of these components leads to a noticeable drop in accuracy.
For instance, without cold start supervised fine-tuning, the model's performance on Visual Probe Hard drops from 44.4% to 25.4%. That highlights the importance of exposing the model to multi-turn agentic trajectories during training.
The overturn masking strategy also plays a key role. Without it, the model tends to answer prematurely, reducing the number of interaction turns and limiting its ability to solve complex tasks.
The authors also experimented with different maximum pixel budgets. They found that both overly large and overly small budgets are suboptimal. A large budget leads to early stopping, while a small budget increases perceptual hallucinations. The best performance is achieved by tuning the max pixel budget appropriately.
Another interesting finding is the effect of the upper limit on turns during training. A lower budget leads to faster initial convergence, but the performance plateaus quickly. A higher turn budget achieves better final performance, though it converges more slowly.
Let's discuss some of the qualitative examples provided in the appendix. One example involves finding the direction of an arrow below the text pranking in a busy city street scene. The model conducts multi-turn reasoning, progressively zooming in, revising hypotheses, and backtracking until it finds the correct answer.
Another example is searching for the number below 67.200 Rizadaharade on a shipping container. The model performs targeted zoom-ins, cross-checks observations, and corrects its path as needed. It ultimately outputs the correct value, demonstrating precise text localization and robust step-by-step verification.
There's also an example where the model is asked to find the numbers on a circular road sign above a triangular sign. It takes 18 reasoning turns, using course-defined zooming and verification across observations, before confidently answering 30.
These examples really showcase the model's ability to handle complex, multi-step reasoning tasks that require exploration, hypothesis revision, and verification.
In summary, mini-o3 represents a significant advance in the field of vision language models. By scaling up both the depth and diversity of reasoning patterns, and by enabling multi-turn interactions, it sets a new standard for solving challenging visual search problems.
The three-pronged approach, constructing a challenging dataset, collecting diverse cold start data, and introducing overturn masking in reinforcement learning, proves to be highly effective.
The implications of this work are broad. It provides practical guidance for developing multimodal models with agentic, multi-turn capabilities, which are essential for real-world applications that require deep reasoning and exploration.
Before we wrap up, let's reflect on the broader context. The emergence of VLMs has been a major milestone in AI, enabling joint understanding of visual and textual modalities. But as this paper shows, there's still a lot of room for improvement, especially when it comes to complex, compositional tasks.
Absolutely. The integration of reinforcement learning, tool-based interactions, and multi-turn reasoning is paving the way for the next generation of intelligent agents. mini-o3 is a great example of how thoughtful system design can push the boundaries of what's possible.
I agree. It will be exciting to see how these ideas are adopted and extended in future research. Perhaps we'll see even more sophisticated models that can handle even more complex tasks with even greater efficiency.
That's a great note to end on. To summarize, mini-o3 introduces a scalable, multi-turn reasoning framework for visual search, leveraging a challenging dataset, diverse training trajectories, and a novel overturn masking strategy to achieve state-of-the-art results on difficult benchmarks.
Thank you for joining us on this deep dive review. We hope you found it informative and engaging. Stay tuned for our next episode, where we'll continue to explore the cutting edge of AI research.
Goodbye, everyone, and remember, keep questioning, keep exploring, and keep learning.